Hello, everybody. Welcome to this Onshape Simulation session. My name's Greg Brown, and I'm excited to be here today with Christopher Gromick and a very, very special guest, Nic Perrin. So today, we're really looking forward to getting into a discussion with Nicholas about his fantastic work on the Perrinn 424 electric hypercar and how Onshape Simulation has been playing a part. But before we get to that, we're going to reintroduce you to Onshape Simulation, tell you a bit of background as to how it works, and do some demos of the key aspects of the product. So let's get right into it. Late last year, we released Onshape Simulation. And before you ask, yes, the world did need yet another simulation tool. We saw a real need for a decision support tool that's built for Onshape designers right into their environment, making it a natural and intuitive part of their design workflow. And to achieve this, we needed three key features. We needed it to be the simplest possible workflow for linear static structural simulation that you've ever seen before. Next, it needed to be an intrinsic part of Onshape itself. And finally, it needed to be available with no barriers for use by professional and enterprise users. Now, we've had fantastic adoption and feedback so far. And looking at some quotes from the forum and other sources shown on the screen here, I'd like to just call out one in particular. That is, Onshape just released native simulation. You've never seen simulation this fast, easy, and accurate. Now, FEA, of course, I've seen what they've done there. Fast, easy, and accurate should be what FEA has meant all along. So, what can we do with Onshape Simulation today? Well, our current focus is on linear static structural analysis. Although, as noted, this is likely to be extended in the very near future with the addition of modal and pre-stress modal types. We provide a nice range of loads, all very intuitively presented, as you'll see in the demos. But constraints are where we really offer a unique and powerful capability, as these constraints are derived from the assembly context, that is, the mates, which of course you already know how to use. We support multiple simulation setups, which are configurable in the simulation panel. And the heavy lifting, that is the meshing, the solve, the adaptivity, is all completely seamless to the user. None of it requires anything to be run on your own computer. No downloads, no drivers, no load on your local hardware. We stream the intermediate results as soon as they are ready so that you can get on with your work, make decisions, and get stuff done. So the way that it works is all very familiar to Onshape users. Parts, that is the shape, are created in part studios where material properties are assigned. Assemblies are then created, which define the context of how the parts fit together and interact. And now you already know how to do this. You just add mates to define the kinematic response, sliders, revolutes, ball, cylinder, and so on. Or not, as the case may be. You can just group things, fix them, or simply leave things in place. Onshape Simulation will interpret all this to create the model to be solved. The most important takeaway from this is if you know Onshape, then you already know Onshape Simulation. But enough of that. On the next few minutes, we're going to take a look at some of the key and unique aspects of Onshape Simulation in a series of demos that we'd now really like to show you. So Chris, if we'd like to move across to demonstration time. I'm going to start with something pretty interesting and just interesting as an engineer. This is part of conceptual assembly from the James Webb Space Telescope. It's part that moves the mirrors around in extremely fine controls. But what's interesting to me is with an assembly like this, how can I create something to study just an individual couple of parts on it? So let's do that. I'm going to create a new assembly. And in that assembly, I'm going to insert just the things that I'm interested in studying, such as the base here and the flexure at the top. Now we've got this new assembly here. I'll simply go over it to it and say, well, let's fix that base. Now it can't move. The next thing I'm going to do is maybe make it transparent so I can see through it, but use one of the loads. Now, in the assembly environment, the only visual difference you see so far is that the loads are up here. So I'm going to use a bearing load on this body and apply it at this face here. Very, very simple. I'm going to just provide the direction for that load and also a magnitude. Maybe 1 Newton is a good place to start for something like this. Now, in fact, that is all we need to do to create our first simulation. So you'll see here it's solving right now. We're doing all the GPU provisioning and all of the good stuff like that. But my computer is really not doing any work other than just showing the results. And I can go up here and have a look at different forms of results. Maybe I'm going to start with the von Mises stress in a deformed animation. Maybe I can switch across to the displacement view. And the displacement's interesting because the real beauty of this mechanism, getting back to some engineering sort of geekery here, is that a small motion here with about 0.6 of a millimeter will result in an extremely small motion at the top here, which is actually what's actuating the part of the mirror. So we're getting like a 50-to-1 gearing down, essentially. But enough of that. Really, what's really been interesting is how easy it is for me to get into and start looking at how this all works in a design sense. The next one I'm going to look at is a little bit more interesting in that it's got a different couple of mates that are defined to create this assembly. Now I'm going to suppress one of these mates here so that I can show you that in the middle here on this journal bearing, I've actually got a cylindrical mate, which allows it to sort of slide up and down in this direction, but also rotate around. I've got another revolute at this other end, which provides the motion to create it in a sort of static, ready for a static analysis. I'm going to immediately start simulating that because we already have a load applied to it on this whole body down here. And again, you'll see very quickly that results start streaming in. And the really important thing for this simulation is how you can see the rotation of this deformable body around the journal bearing. If we had just fixed this fully, we would have artificially constrained this both in this direction, in the Y direction here, as well as the rotations from before. Now, there's a really interesting thing that I'm going to point your attention to if you're already familiar with Onshape, is that there are other people in this document as we speak. So like any good demonstration, I'm going to reveal what's behind the curtain, and I'm going to reveal that Chris actually is in this document, and I'm following him as we speak. This is a really key aspect of Onshape simulation in that we can run this simultaneously or collaboratively, unlike anything else that's possible. So Chris is actually doing an edit to one of the cutouts in this, and you see as soon as he made that edit, so the screen on the right is Chris's screen, and I'm just following him. The screen on the left is my own screen right here, and I can see that as soon as he made those edits, they're represented and an update in real time. So this kind of real-time collaboration can unlock a whole bunch of new workflows, paired programming almost for static simulation. It's pretty amazing and really only available in Onshape simulation. So the last thing I'd like to show you is, if I just move my screen back this way, is this simulation. Now, I've already got some results on it, but what I will do is reveal that this wasn't just a normal piece of geometry. This is actually a mesh. Now, the mesh was imported and created from an external program, actually some technology that PTC, in fact, owns. And what I've been able to do in Onshape is use the mixed modeling capabilities to take that mesh model, which came in as an STL file, and further cut it out and create basically analytic faces like these ones in here in order to create an assembly of other components and maybe even make modifications to the mesh by adding in material that didn't exist in the original mesh. So if I show the results back on that, you can see it's a nice simulation here. And it's pretty amazing. It's so seamless that we can use meshes or B-rep parts interchangeably. It makes no difference to us. The other interesting thing here is that, and to introduce some of you to, is that we have this thing called the simulation panel, which allows me to set up, configure, and control different simulations, maybe different load cases that I've been interested in So I've got a couple of different simulations here, and I can flip between them and look at the results there. And finally, the last thing I'd like to show you is that these numbers that are being applied as loads in the components of the loads in the simulation are actually special. If I click on them, you'll see that they're expressions, the fx times 2 or the fy times 1.5. And in fact, as you've probably already guessed, these are coming from variables that are defined in a global variable or in a variable studio. Just another example of how well and how intrinsic the Onshape simulation is with the rest of the Onshape product. So Chris, that's just the bare scratching the surface. Why don't we hand back to you and have a deep...
Right. Thank you very much, Greg. Okay, with this simple assembly, we're going to show you some complex use of mates with Onshape simulation. Now, the parts on screen are mated as you might suspect, with one exception. This locator here is kept in place with a planar mate between it and the housing. The load I've assigned is to the push rod. As I move the locator, you'll notice that the load too moves because Onshape simulation is Onshape and everything updates as you would expect. At any time, I can show results, and the results that I'm going to get on screen are going to look kind of boring, to be completely honest. But what's surprising is the fact that it's simulated at all, because if you were paying attention, I didn't actually fully constrain the system, at least not through the mates. The way I've done that is through a special use of our implicit interactions. And I can show the connections over here in the simulation setting part of the simulation panel. Here, because I didn't have a mate specified between the locator and the ground, Onshape simulation inferred one because they were within proximity, and I've set that as my default method. That allows me to use other Onshape capabilities, like name positions. So I can just go back to top dead center whenever I want. And of course, Onshape simulation is going to update. Now, in reality, this housing is not going to be just fully fused to the ground. It's going to be bolted there. So in order to simulate that, I can use a simulation connection and limit that fasten mate just to these 4 regions. But because mates are configurable, I can also just skip to the configuration and show you that now I'm only going to be fastened at the 4 corners. If I show you the results here, we're going to see something different. But to show it more clearly, I'm going to jump to an exploded view. If I look from the left and animate, I'll see even at this exaggerated scale, I'm getting way too much warping, and indeed, I'm exceeding the yield strength in each of my 4 corners. It appears I'm going to need to go from a 4-bolt to an 8-bolt configuration. And these results are going to come well in line with my design intent. And that's really the intention of Onshape simulation, is giving you analysis-led feedback early in your design process. Now, admittedly, this is a bit of a simple assembly. So let's look at something more complicated. All right. This robot here might sit in your warehouse or your factory. And what we're going to focus on is the gripper, the end of arm tooling that sits here, and it's going to pick up tools along your assembly line. If I jump to that subassembly, you'll see that I've made some simplifying assumptions, mostly that the housing is fixed to ground. And that's because what I want to investigate now is what happens if I put the full compressive strength on the driver to whatever I'm going to pick up. Now, just because I've fixed the housing doesn't mean that I've fixed everything else. These are still kinematically related. And my assembly is just about complete with one obvious exception. I'm missing the tool to be simulated. So let's insert that here. Now, I've gotten this file from a colleague, and I'm a bit frustrated because it came in as an STL. And I really don't want to go through the pain of assigning mates or pinpointing each one of these facets. But the good news is with Onshape simulation, I don't have to. I just have to get it close enough. So if I eyeball this as touching, all right, then I can go back to and show those connections. And Onshape simulation, again, is going to infer that the gripper fingers here and the ring tooling here are going to be stuck together as we drive this driver here on the plunger side. Now, I've hidden a couple other inferences. All right. I've got standard content in the form of these 8 bolts, and those 2 have connections inferred with the sliders here. All of my other mates, though, are respected as I've defined. At this point, I'm just about ready to launch a simulation, but I've forgotten one key aspect. I'm missing a material. Now, I could go back through my part studios and try to figure out which one it is, or I open my bill of materials, and lo and behold, it's that same last part that I just introduced. Now, I've been told that this is going to be made out of 3D printed tungsten, so I make that one correction. Now I'm ready to simulate. All of this is possible because of our unique behind-the-scenes adaptive meshing scheme that allows us to infer connectivity and apply interactions specifically from the mates without you having to go through that conventional analysis step. And it really frees designers from having to become analysts. Now that I've got early results, I can see that as long as I have a careful driver at the wheel in the warehouse, this tool is going to be fine. Now, that's everything you can do in a nutshell in Onshape Simulation today, but I wanted to show you one thing that's coming right around the bend. You may have seen this particular model before, but it's a drive shaft, and if I animate it, you can see that it's fully articulated across both double Cardan flanges. All right. If I show you these connections, we'll see that it's mostly made up of revolute mates with one long slider mate at the telescoping shaft in between. If I was to try to simulate this the way that Greg and I have been doing up till now, I'm going to run into two problems. First, I haven't assigned a load. So linear static structural analysis doesn't know what to do. Second, this is not fully constrained. But neither one of those is a problem for the simulation that I'm about to run. And for the first time ever, I'm happy to demonstrate to you modal analysis coming to you in Onshape Simulation. What we should be seeing on screen here shortly is the result of an eigenvalue analysis of the unforced equilibrium state of the system. In other words, this is a free response solution. And we're going to deliver to you the natural frequencies or harmonics of the assembly. So when we saw before that we had two free ends, we're going to expect that that first mode shape is indeed going to revolve around those two free ends. In between, we're going to see that the shaft rotates along its cruciform universal joints. Now, not to over-exaggerate things, I'm going to change the deformation scale and animate. And indeed, as you can see, everything works as you would expect, with these natural harmonic series getting higher and higher in frequency. The fourth one's interesting in that we have counter-rotating ends on either side of the shaft. And the last one is subtle in that we have that telescoping shaft sliding along its center line. Now, there's still much work to be done before this can reach your hands, but I wanted you all to know that we're working hard to improve Onshape Simulation each and every week. Now, speaking of people who are working hard, it is now my pleasure to introduce to all of you Nic Perrin of Perrinn 424, who's going to talk about his work making the fastest electric hypercar ever. Nic, thank you for joining us.
Thank you, Chris. Thank you, Greg, and thanks Onshape for having me today and the opportunity for me to talk to you about 424. I want to start telling you that the aim for 424, I have set the aim to develop the fastest electric hypercar in the world in a new way. And I'm going to explain to you what I mean by that. Short term, the mission for 424 is to go and set a lap record, a new lap record at the Nürburgring in Germany, and show that our team can compete against established organizations like Porsche. Porsche, indeed, has set the current lap record 5 years ago with their 919 hybrid. And with the 424, we are going after them. How and why are we developing 424? Well, the first point I want to talk about is 424 is developed on the internet using the power of the cloud. And I grow a network of talented individuals, software developers, designers, engineers that I have met on the internet. and bringing now great companies in our network like Onshape and PTC. This, for me, allows a faster innovation process in the virtual space. The second point I want to make is we are committed to share the Perrinn IP open source with the public. The reason is because I want to leave 424 to the public, to inspire a generation of engineers to collaborate on a global scale. I've got 20 years of experience at the highest level of motorsport. I've worked in Formula One, in Formula E, at Le Mans 24 Hours. I'm using this experience to develop 424, but I also want to share my knowledge, and I want to advance the way we innovate, collaborate, and communicate. For me, innovation is a global challenge, and it's a challenge that we can solve, and we need to solve with software. Why using Onshape? For us, Onshape is an ideal partner. I discovered Onshape a few years ago. I personally love designing in Onshape. We have committed the project and 424 to be designed exclusively in Onshape. And you can follow live, in fact, our designers through public documents in Onshape and follow the design of 424. Speaking of design strategy, I touched on the fact that our team is fully distributed. I've got engineers working from 10, 15 countries. We have an open source strategy, so everything we're going to design is going to be shared with the public. And the cloud-first strategy. It's much easier for me to use simulation tools that are built native in the cloud, allowing our team to work seamlessly together. As I said, the car is fully designed in Onshape, and I'm sure many of you have already found some of our documents in Onshape, in the Onshape community. We have a 95% simulated digital twin strategy. What that means is the whole project really is going to happen 95% in the virtual world, and only at the very end, we are going to build the final and best version of our model to go and set the record at the Nürburgring. In terms of performance, this car, as I said, needs to be the fastest electric hypercar, the fastest hypercar, full stop, in the world. The top speed of the car is 360 kph. In fact, we are limiting the speed. The car could go faster than that, but we are limiting the speeds in order to save a bit of energy and have an optimum size of the battery system around the lap of the Nürburgring. The acceleration is mind-blowing, 0 to 100 kph in just 2 seconds. For the electric powertrain, we are using Formula E technology. We are using 3 MGUs, 1 at the front, 2 at the back, giving us an optimum power distribution of 33% at the front. It's a 4-wheel drive car and a total power of 750 kilowatts. It's a nearly 1,000 horsepower. We need to keep the weight of the car to a maximum of 1,000 kilograms. This is one of the main parameters for our record. And this is where Onshape and Onshape Simulation is helping us to lightweight the car. Half of the weight is from the chassis and half of the weight is from the electric powertrain. And as you know, electric technology can be fairly heavy. We're keeping the weight of the car under 1,000 kilograms. Today, we have a dynamic simulation that we have a test driver driving it in the virtual world. In fact, this simulation is available on GitHub open source. You can download it and install it on your PC. And even drive it yourself if you have a steering wheel. But even with a PC, you can launch the autopilot mode and see the car going around the Nürburgring. This simulation is also installed on one of the best motion platform in the UK, used by Formula One teams. So we have here the best possible simulation tool to predict our performance. We are predicting today a lap time of 5 minutes 07.5. going around the 20 kilometers long Nürburgring track. And to put this in perspective, remember we are going after Porsche, and Porsche has set a record of 5 minutes 19 seconds. So we believe we are just a bit more than 10 seconds faster than them using this simulation tool.
So, Nic, just to ask, that's not your best lap time, is it?
No, personally, I really enjoy driving the car. I've done some driving before, but I can be maybe 10 seconds off a real professional driver. We have in the team our test driver doing a lot of testing for us, hundreds of laps. And that person has set the current lap. And every time we have a new version of the car or a setup to test, we will do some new driving. That's how we proceed.
Well, we're going to post the link to GitHub in the chat so that anyone watching, if they can beat this record, they should probably contact you, right?
Yeah, 100%. If anybody wants to drive the car, again, it's free, open source, go on GitHub, drive the car. And if your performance is close to what we're already setting, there's no reason why you wouldn't be able to integrate our team. This is how it works. So we are now going to dive into how we use Onshape Simulation to lightweight the car. Remember how important this aspect is for us. We're showing you a few examples here. So we're currently using Onshape Simulation to design our front and rear suspension system. Here you can see the upright holding the wheels. We're also integrating the wishbone, so the full suspension assembly. And Onshape Simulation can cope with this. And also another example is this casing in the middle of the car, which is quite a complex component here. And we're going to dive into how we use Onshape Simulation and how we go about it.
Now, Nic, you said that 95% of this car is simulated before anything gets built. Obviously, linear static simulation in Onshape is not going to do that full 95%. So you must be well equipped to use a bunch of other simulation tools, are you not?
Absolutely. We need to simulate as much as we can of the car. 95% means things like aerodynamics. This is one of the key parameters for the car. So we do heavy CFD analysis for 424. This is one, if not the most performant car in terms of aerodynamic performance that I've ever worked on. It's an unregulated car, so we can push the envelope a lot on 424. So CFD is one example. We do thermal analysis. Electric powertrain, as we know, heats up quite quickly. The lap is 5 minutes. So as an example, the battery starts as cool as we can, maybe 15 degrees. And at the end of the 5 minutes, we need to make sure it stays below 70 degrees. And we have accurate simulation of what the battery temperature will be. Again, all of this is important to design and dimension, for example, the cooling system of the car. These are only two examples. We do stress analysis, obviously, around the car to lightweight. We do electromagnetic analysis for things like electric NGUs. So simulation is everywhere. And that's where the digital twin model is for us.
And when you were doing some of the stress analysis, at what point in using Onshape Simulation did you feel comfortable that it was going to be roadworthy for your designs?
Yeah. So as the leader of 424, and given my experience, I want to make sure we use simulation tools that are proven or accurate because we rely on them for our key decisions. So we went through a benchmark process of Onshape Simulation. We effectively compared for a bunch of components on the car what Onshape Simulation would give us as a result versus two other established software on the market. And we found that the results were really close. In fact, inside 10% for displacement stress, which is actually completely standard across a variety of software. So I was completely happy with that. And at that point, we decided that we are committing 424 to be stressed by Onshape Simulation.
Well, I know that the CRASHBOX encasing has been a project for all of us on this call. So why don't you tell us a little bit more about what the engineering details of it are?
Sure. So here you can see a bit more where this casing is located on the car. And we have a design strategy of building this casing as a combination of a laminated carbon shell, which is transparent on the picture. It's the gray part that you see in the car. That's got a constant thickness, and it's a controlled, simple shape where everything else will come and be bolted on. But this is not enough. Inside, we're going to have a metallic, most likely aluminum insert, which is this organic shape that you see. This is fitted inside the carbon shell, and the combination of the two is giving us the rigidity, the strength, and the stiffness we need. So a combination of, it's a hybrid, if you like, of a traditional laminated component with molds, and using the latest manufacturing technology like 3D printing for the metallic inserts. In terms of load casing, and that's where the beauty of having so many different simulation tools, we are taking from our dynamic simulation that our test driver is using to go around the lab. We know the loading from every single part of the suspension feeding into this casing. And we're isolating the maximum cornering loads, as an example, and some of the impacts also. And that's giving us the worst case for that component, okay? So that loading is going to then be used as our sign-off process for designing this component into Onshape. We are using generative design, and we're going to see a bit more about this in a second, for the insert to give us the optimum strength to weight ratio. And again, for us, we need a certain level of strength and stiffness and the lightest possible component. And we are confident that Onshape Simulation is giving us the best solution for that. And the last point I'm touching on here is we were really pleased to see how slick and quick the process was to use Onshape Simulation. One of the key things for us is we were able to use directly STL geometry, which we know is the geometry coming off generative design, feeding back into the Onshape simulation without having to redesign or clean up the geometry. So just saying that the process for us, we gained a lot of time and it worked really well.
Well, Nic, we've prepared a short demonstration of that process. Would you be willing to talk us through it?
Of course. Okay, so here you see the back end of the car, the assembly that comprises of that casing I talked about, and inside we've got the two MGUs connected together and connecting back to the drive shafts going to the wheels. You also see the yellow pads on the side, which will connect the suspension system on the side of the casing, and also the pillars going up and connecting to the rear wing. We are now going to go and focus on this casing we want to design. Here we are in the assembly context. We are putting the loading that comes off our dynamic simulation I talked about. So the suspension loads and the rear wing loads. And now we're going to perform a first simulation where we use only that shell, but without the insert. And we can see very quickly that this is not realistic. The displacements are way too high. That component would fail, in fact. So we need to go into fitting the insert inside that shell. So the second simulation is looking at, this is the volume that the insert will be able to use. We're checking here that all the connections are made automatically between the insert and the shell. And that's all working and ready to go. And that volume is going to be reduced as much as possible, but still having the stiffness and strength that we need. This is one of the solutions that topology optimization from Onshape is giving us. That's the lattice structure that would require a full 3D printed manufacturing process. So one of the possible solutions for the insert. And we are going to look at the second solution, which is a little bit more simple, plain section, organic shape still, but this could be 3D printed or slightly redesigned into a 5-axis traditional machining process.
So Nic, sorry to interrupt, but I'm already seeing some of the questions come in. Yes, there are plans eventually to have generative design in Onshape, but we're making no commitments as to when that will be released. Nic's been working closely with us as a partner on 424 project, and that's why he's got a sneak peek at some of that technology.
And here what we're seeing is we've been feeding back the that solution, that organic shape, back into the static analysis, just checking that we get the stiffness we need. And as you can see, there's no more red, failure areas in that component. So we're happy with the results. And looping back into the complete assembly, and you can see that we have something that works, that insert is clearing all the internal components. And effectively, that final assembly is the solution for us. We are switching to another assembly of the car, the rear wing. You can see the two pillars, the DRS system on top, which is 2 pneumatic actuators that will open the flap in a straight line to shed a bit of drag and go faster. What we are doing here is a model analysis, so checking the potential oscillation around the natural frequencies of the rear wing. We are looking at 5 modes here. We are on the second one. The idea is we want to make sure the excitement from the chassis and the roads and the suspension is not going to match the natural frequency of the rear wing and go into this uncontrolled oscillation that could lead to a failure of the assembly. And that's the mode 4 here, and the final one. So we have criteria on minimum frequency for each of these modes to make sure we are not exciting them.
Well, thank you very much, Nic, for that. You certainly made Onshape Simulation look very capable.
Well, thank you. I mean, for us, again, as I said, it's a fantastic tool to use for 424, so we couldn't be happier to use integrated Onshape tools.
And it's also been the kind of project that a lot of us have loved to get our hands dirty on, and this is such a great thing for us to be collaborating on. Yeah.
Thanks, Greg.
Yeah.
So now we've actually got a little bit of time to answer any questions from the audience that haven't been answered already.
Okay, there's one question here. Maybe Chris, we can dig into, and the question is about there is definitely. It says I assume that there's a mesh being used to complete the simulation on the server side. Will there be an option to view the mesh being used in order to give the designers more information to make decisions with? Let you have a crack at that one first, Chris.
Sure. The answer is yes. There is most certainly a mesh. We are running finite element analysis. But no, we're not planning on a feature that would expose that to you. The adaptivity that we use behind the scenes is really part of our secret sauce, and it's something that we want to keep proprietary.
Yeah. All right. There's another one that came in earlier, and I wanted to just get back to, and that is, do you plan to support simulation at the part level? I can take this one. In fact, we have made a conscious decision to put simulation in the assembly context of Onshape, because that really, as I said, the assembly provides the context for a part or many parts, how they fit together, how they work in terms of the assembly. So no, we don't intend to put the same loads and other controls into the part studio. The part studio remains a place where you create the geometry. The assembly remains the place where you use the geometry. And in our case here, using the geometry means creating a context and performing a simulation.
And Nic, this is a question over to you. I'm seeing a lot of people in the chat who are wanting to know more about how to get involved with Perrinn 424. How can they reach out to you and get involved?
Sure. Yeah. Thanks for the question. So 2 ways, really. So the first one, we go on LinkedIn. This is the social media platform we have chosen for the project. follow myself and the Perrinn 424 page, and that you will have all our latest news. The second point is, please go on perrinn.com, register, and this is where you will see our core team of developers interact. It's a chat system, communication system, and you will be able to follow and talk to all of us, all our team members and myself. And you'll also be able to invest in the project directly if you want to.
All right. Well, talking about investments, Greg, this is a question over to you. As Onshape continues to invest in Onshape Simulation and broaden its capabilities, should users expect to have to pay more for those?
Well, yeah, that's an interesting and good question there. I mean, it really depends on what the directions we go and what we continue to bring. There are costs involved for us to bring the service. As I said at the beginning, our initial and where we stand is that we want a design tool, a decision support tool to be available to our users. If we do go into certain directions that require different amounts of compute, then perhaps it's something that we would consider offering as an advanced simulation option. But those decisions haven't been made at this point, and we will continue to evaluate that.
And we've been seeing a lot of questions about CFD. CFD is one of those extremely computational analysis methods that you purposefully didn't see on kind of our coming soon slide earlier in the presentation. Yep. Okay, Nic, this is not the last time we're going to see you. Is that correct? We should be seeing more of you pretty soon.
Yes, indeed. So I believe in May we have the LIVEWORX conference, and I will be coming and talk about 424 again on stage. So I'm really excited about this, and I hope to see many of you there.
Well, Greg, you're a veteran of LIVEWORX, so maybe you could tell everyone a little bit about what they can see if they do come and join us there.
So let's just bring up that next slide. We can cue off some of that because there's some impressive numbers. For LIVEWORX 23, yeah, as Chris said, I've been to a number of these events. I've been at PTC many, many years, and you know, when we transitioned into the LIVEWORX approach, it's just been an incredible event. What you will definitely see is a huge demonstration. So we call it the Extropolis, where people like Chris, myself, Nicholas will be there demonstrating live. Having as many conversations as we can during the the days of the event, but you can just wander around. You can see a picture in the background there of just a tiny part of the floor, which will be taking up tens of thousands of or more of square footage in the conference area. It's a really, really exciting time to come and challenge product managers, challenge developers, other executives at the company, fellow users. Try out some of the software. There's likely to be some additional things that we can talk about and maybe even give you a little sneak peek of it too at the same time. So if you haven't already heard that there is a special offer for some of you, if you're quick enough to register and get your sort of complimentary all access pass to the event. If not, you'll still have a great time. So we encourage everybody to do that. And at the same time, from myself, and thank you for attending this session. It's been great. It's been very, very interesting. We will be able to follow up with some of those extra questions. So feel free to submit some more things. We will watch them. I'm sorry we haven't been able to get time to everything today. But once again, thanks for attending the session, and hopefully you can enjoy the rest of the event. Thank you very much.
Thanks, everyone.
Thank you.